as we get started today, some quick questions for you to answer. So go ahead and have just a sheet of paper. Let's have one sheet of paper out. Let's see how we do answering some questions. This isn't a quiz, just a quick review, see what we remember. Just about one sheet of paper and a pen or pencil, preferably pencil. That's mainly what we use in this class, but some quick questions for you. All right, number one, what term refers to the likelihood that a particular event or particular events will occur? What term refers to the likelihood that a particular event or particular events will occur? If we're trying to find the likelihood of either one event or another event occurring, what mathematical operation should I use? Addition, subtraction, multiplication, or division? If I'm finding the likelihood that one event or another event will occur, what should I do with the individual likelihoods? Add, subtract, multiply, or divide. Number three, if I'm trying to find the probability that two different events will both occur, first one, then the other, what operation would I use? Addition, subtraction, multiplication, or division? If I'm trying to find the likelihood that one event and then another will occur, I would use addition, subtraction, multiplication, or division. If I'm trying to find the likelihood, number four, that either this event or this will happen, and this event is distinctly different from this one, there is no overlap, then we would say that these two events are considered to be blank, two words. If this event and the other event are two totally separate, there's no overlap between them, we would say that the events are blank. From yesterday's lesson, if we're talking about the probability of first this event and then this event occurring, but this first event in no way affects the likelihood of the second event, then we would say that those two events are blank, one word. If the first event in no way affects the other, then we would say that those two events are blank. For instance, we said you flip a coin, it could be heads or tails. Well, if you flip it a second time, what you got the first time has no weight or bearing on what you get on the next flip. So those two events are blank, one word. All right, for the next three questions, I want you to imagine we have a single die we are rolling. We're going to roll it twice. What is the likelihood that the first time I roll, I get a 1, and then the next time I roll, I get a 6? Find for me the likelihood that the first roll gets me a 1 and the second roll gets me a 6. I want the likelihood of both of those events occurring. For the next question, suppose on the first roll I want to get a 4. And on the next roll, I just want some even number. I'm not picking which one, but I just want an even number on the next roll. What's the probability I specifically get a 4 on the first roll and then follow that with another even number on the second roll? What's the likelihood that I get a 4 followed by an even roll? And for the next one, for the last question, what is the likelihood that my first roll is an odd number and the second roll is an even number? What's the likelihood that the first roll is an odd number and the second roll is an even number? I'm going to roll the die twice. Likelihood that the first roll is odd and the second roll is even. What is that likelihood? All right, let's see how well we retain some of these things. Number one, class, what do we call the likelihood that an event or events will occur?
Probability.
Probability, good. For the next question, we said that if you want to find the probability that either this event or this event occur, anytime we're finding probability with or, we should add, use addition. Good. We said if we wanted to find the probability that first this event and then this next event will also occur, we said we would want to use multiplication. I said if we're trying to find the probability this or this occurs, but there's no overlap, they're distinctly different, we said we would refer to those events as being mutually exclusive. And I said, well, what if we want the probability that first this event and then this event both occur, but the first event has no weight or bearing on the second? We would describe those events as being independent events. That's what we had in the next examples. We're all independent events, weren't they? What I roll the first time has no weight or bearing on what I roll the second time. So rolling a 1 class is a 1 to 6 probability. Rolling a 6 is 1 to 6. What's the probability of then 1 and then 6?
1 to 36.
1 to 36, as we multiply when we have that word and. What if I said, what's the probability I roll a 4, and then I follow that up by rolling some other even number on the next roll? Well, what's the probability of 4? 1 to 6. What's the probability of an even number? 3 to 6 or 1 to 2. So what's the probability of 4 and then another even number? 1 to 12.
Yeah, 1 to 12.
1 to 12. 1 to 6 times 1 to 2 is 1 to 12. It's okay. I messed up a couple times the last couple lessons, so I can't hold you, too hard against you. What's the probability I roll an odd number, and then on the next roll I roll an even number? Well, what's the probability of odd? 3 to 6 or 1 to 2. What's the probability of even? 3 to 6 or 1 to 2. So the probability is 1 to 4. 1 to 4. How'd we do?
I don't know.
Got them all?
Yeah.
Got them all? Missed a couple of them. Right, questions on any of those? All right. Look in your textbooks if you would at page 393 now. And we kind of previewed this yesterday. We talked about independent events, but it already kind of previewed, using our bulletin board over there, the idea of dependent events. Dependent events occurring. Well, if you want the probability of one event and then another, we're still going to class multiply. And implies we have to multiply the two probabilities together. However, if the events are dependent, then we must assume the first event has occurred, and then it will affect the second event. For instance, looking at the bottom of page 393, we see Amanda and the marbles. Okay, Amanda had the 5 red marbles, the 3 yellow marbles, the 2 blue marbles, right? And we said, what's the probability that Amanda draws a blue, puts it back, and then draws another blue? Remember from yesterday? Well, the idea is if she puts it back, then the probability the second time is the same as it was before, right? But what if she doesn't put it back? Remember, there's only 2 blue in there. Well, the probability of drawing the first blue, well, there were 2 out of 10, right? So that's a 2 to 10, or we could say 1 to 5 probability. But if the probability of the next blue, after having already drawn a blue marble, there's not 10 marbles anymore, class. There's only 9. And how many of them are blue now? 1, because she already drew the first blue out, right? There were only 2 to begin with. So she draws one of the blues here, 2 out of 10 chance, but now there's only 1 left out of 9 total now marbles. What's the probability of drawing blue, not putting it back, and then happening to draw the other blue marble out? 1 to 45. Does that make sense? The lower number, again, technically this was a 2 to 10 originally, right? So we can see that the lower number is going to change. There's fewer items available. We see that with the cherry cordial and maple fudge, right? 74 candies to choose from, but once you've drawn the cherry cordial out, there's now only 73 candies to choose from, right? Well, if I wanted, for instance, both cherry cordials, the first cherry cordial is 2 to 74. What's the next cherry cordial? It's not 2 to 74.
1 to 73.
1 left out of 73. Does that make sense? If I wanted, let's see, there were, it looks like there's 6 cashew clusters, right? Okay, so on the first draw, if all the candies are there, they're all dumped out, I just reach in and I grab one. What's the probability of cashew cluster if there were 6 of them out of a 74 total, class? 6 to 74. But what's the probability the next draw is also cashew cluster?
5 to 73.
5 to 73. You see both numbers went down. Now what's the probability of another cashew cluster?
4 to 72.
Because they both keep dropping. Now, if I were to then switch and say chocolate whip, there's 2 chocolate whips still, right? None of those have been taken yet. So now if I then want a chocolate whip, that's 2 to 71. This number continues dropping as more candies get eaten. But this number is still 2 because none of them had been taken yet. It just requires a little bit more thought. You have to keep track of what's still in the bag or what's still on the table, what's still available. Does that make sense? So a little bit more thought just to keep track of, but you're still just multiplying and getting really big numbers, which I'm not going to do. All right, not right now at least. All right, so turn the page. Turn the page. And there's a comparison here, right, of the Amanda versus Brian. Okay, so Amanda draws a blue marble, puts it back, and draws another blue marble. Notice with Amanda, with replacement, they are independent events. So that's why probability of blue the first time is 2 to 10, probability of blue the second time is 2 to 10, probability is a 4% probability. That she'll draw blue, put it back, and then draw blue again. Right, could be the same blue, could be the other blue. For Brian, however, with the dependent events, he draws the blue, but he doesn't put it back. So now there's only 9 marbles, of which only 1 is blue. Now it's 1 to 9. We see that 1 to 45 that we talked about. I guess it was Brian, not Amanda. I can't read. Notice it's only a 2% chance. The odds dropped considerably. Do you see that? Technically, it's rounded up to 2%. It's not even quite 2%. All right? So with dependent events, the probability of one event and then the next event happening is, well, whatever the probability of this one is, and then what times the probability of the next one, given that the other one has already occurred. Make sense? Look at the example, problem 8.6. Read the problem for us, if you would, Lana.
Fish tank. Wait. A fish tank contains 9 clownfish, 3 crabs, 7 pufferfish, and 2 starfish. They are removed one at a time. They are removed one at a time at random, so the tank can be cleaned. What is the probability of first removing a pufferfish and then a crab?
All right. That would be a really random assortment in a fish tank. I'm just saying. But they all sound cool. I'm not a fan of them using crabs and clownfish because now, which one is C? You know? Like, wish they hadn't chosen 2 C words. Like, I can use P for pufferfish and S for starfish. But I guess CR is crab and CL is clownfish. I don't know. Anyway. They say, what's the probability of a pufferfish then a crab? So notice the way we could write this is the probability of pufferfish times the probability of crab after, I'll do CR actually, crab after pufferfish has been removed. Well, how many total critters is in that tank?
21.
21, right? 9, 3, 7, 2. It's 21 critters. All right, how many of them were pufferfish? 7. So, if the odds of just reaching in the tank and choosing to pull out a pufferfish is a probability of 7 to 21, which I want to reduce down
1 to 3.
1 to 3. There's a 1 to 3 chance I pull a pufferfish out, right? Now that I've pulled out the pufferfish, how many critters are still in the tank, class? 20. How many of them are crabs?
30.
Still 3, right? There were 3 crabs all along. That hasn't changed. Now, there's only 6 pufferfish left, but I'm not asking about another pufferfish. I'm asking about a crab. So there's 3 crabs left in the tank. Does that reduce? No. So we're going to leave 3 to 20. But I'm not going to multiply until I've canceled first. What's the odds of pulling out a pufferfish then a crab?
1 to 20.
1 to 20, assuming no replacement. That's the key. I don't toss the first pufferfish back in because the whole point was get him out of there so I could clean the tank, right? Not just pulling out critters for the fun of it, especially not a crab. Any of you ever been like clawed by a crab? Nobody? Okay. I was going fishing with my dad one time, and as I was reeling in my line, I realized I had a small blue crab about this big caught on my line. So I went to take him off, and my dad's like trying to tell me how to get him off, and I wasn't listening. I'm a high school kid. You know, just take the crab. No. You don't just take the crab off. He grabbed onto my thumb and tried to shake him off. His arm ripped off. The claw was not letting go. Now, it didn't hurt that bad. It hurt a little bit. You got something grabbing onto you real tight. Couldn't even shake it off. And, of course, a little bit of blood. Not bad. But there's the rest of the crab. I'm kind of kick him off of the dock where we're at. Well, anyway, no lie, a little bit later, we haul in another one. But this one's this big. I ain't touching that one. That claw on that thing was this thick. I'm that could probably take my thumb off. The first one's tiny. That one, I'm messing with the crabs. So I don't know whose big idea was to put crabs in the tank in the first place, unless your plan is to use a little net thingy and drop them straight into the boiling water and get some steamed crab. Like crab meat is amazing. I love crab meat. Crab legs, so good. But I don't know about taking one out of the tank. Not reaching in and grabbing it anyway. All right, go grab that. All right, look at the next page. What's the probability that the first 3 removed are all the crabs? Now, if it's me, they're the last 3, and I'm going to get off. I'm going to be like, my shift is going to end before the crabs come out. So, Scott takes over after me. Okay, let him deal with the crabs, because I'm a jerk like that. But anyway, so here, look at the way they set it up. They want probability of C, crab. Then they want the probability of crab after crab. Then they want the probability of crab after crab. Okay, so let's follow this through. How many critters in the tank, class? 21. Of which 3 are crabs. But after we take the crab out, now there's only 20 critters, of which 2 are crabs. And then once we take that crab out, now we've got 1 crab out of 19 critters now. If we reduce, then we end up with 1 to 7 times 1 to 10 times 1 to 19, which is 1 to 1,360? 30. I can't do math. 1 to 3,330 chance of crab in that order. All right? Now that, by the way, that eliminates the human element. Some people are like, let's do all of this, then let's do all of this. How many of you, when you eat, like you eat all of the vegetables, then you eat all the potatoes, then you eat all the meat? Okay, how many of you are, I'm going to get a little bit of potatoes with a little bit of meat, then I'll have a few bites of vegetables, then I'll go back to the potatoes. All right, so those of you who are, no, I'm going to eat all of this, then I'm going to eat all of this, then I'm going to eat all of this. You people, you have a much higher probability. Okay, this is assuming totally random. Okay, maybe it's 3 different people. Somebody go pull something out of the tank. Maybe it's blindfolded. Ah! Okay, we got 1 crab out. All right, next person blindfolded. Pull something out of the tank. Ah! And the third guy, you hate to be the third guy, like, what's in there? When I'm blindfolded, I can't see. I don't know. Maybe that's, I don't know. Maybe the probability of crabs is higher because they grab back. So it wasn't so much that you chose the crab. The crab chooses you. It's like the force, right? The force chooses you. Anyway, the crab chooses you. I don't know. Anyway, I digress. Letter C. Go ahead and read that part for us now. Now what are we finding? Joshua?
What is the probability that neither of the first 2 animals removed are clownfish?
All right, so here we want no, they use CF for clownfish, I see. We're going to find the complement of clownfish. All right? Now, how many clownfish in the tank, class?
9.
So how many ain't clownfish?
12.
Out of 21 critters, 12 ain't clownfish. So the probability of pulling something out that ain't a clownfish is 12 to 21. But then you get ready to go in and grab another thing out. Now how many critters are in the tank?
11 to 20.
Oh, 20, right?
Or 20.
And if you pulled a non-clownfish out, and there were 12 non-clownfish to begin with, how many still ain't clownfish?
11.
There's 11 that still ain't clownfish. Of course, we could do a little bit of reducing here, right? Knock a 3 out to get
4.
And we get to cancel a 2 with the 4 and the 20 to get
1.
oh, actually, it's a 4, not even 2. It's 4 to get 1 to 5. Good call. And that gives us a probability of
11.
11 to 35 that I don't pull clownfish either of my first 2 times pulling something out. Questions on part C? Does it make sense? All right. There's a little summary box there for these compound events. Probability if there's A or B, right? A or B. Notice they're adding. Probability of A plus probability of B. If they're not mutually exclusive, remember, it's still probability of A plus probability of B minus the probability of both of them. If they're independent events and you're finding A and B, notice you multiply. But if they're dependent, you have to account for B after A has already occurred. So kind of a summary of those formulas. Any questions on that? All right, let's do a little bit of review here. Number 1, we're supposed to determine, first of all, whether you would add or you would multiply. If you're adding, the question is, do we have to subtract any overlap? Are these mutually exclusive, or do we have to subtract the probability of both? So let's look at letter A. The probability of drawing 2 yellow marbles without replacing the first. All right, that means yellow and then another yellow. Would we add or would we multiply? Scott? We would multiply. The yellow and then another yellow would have to be 2 separate things both occurring, right? So both occurring is an and, that's a multiply. Now, is that going to be dependent or independent? Dependent. If you don't replace the first marble, then you've changed the probability on the second one, haven't you? Questions on number 1. Let's take a look at number 2. Rolling a number less than 4 or an even number on a 6-sided number cube. Rolling a number less than 4 or rolling some even number on a 6-sided number cube. Lana, would we add or would we multiply?
You add.
How do you know to add?
Because it says or.
It says or. Now question, Lana. Less than 4, even number. Are those mutually exclusive or is there some overlap that would have to be subtracted?
There's overlap there.
There is overlap. What number or what numbers are both even and less than 4?
Wait. 4?
Well, 4
Wait,
isn't
what?
less than 4.
What'd you say?
What number or numbers are both even and less than 4?
2.
2, right? 2 is even, 2 is also less than 4. So you'd have to subtract that overlap away if you were finding that probability. Looking at number 3. Drawing a letter D or drawing a vowel from a bag of letters. Joshua, would we add or would we multiply?
Add.
Because of the word or. Okay, now, D and vowel, are those mutually exclusive or is there overlap that would have to be subtracted away?
Mutually.
They are mutually exclusive. We don't have to worry about overlap. Number 4. Flicking a spinner and getting a number 2 twice. That means flick spinner, get 2, flick spinner, get 2. Would we add or would we multiply? Class? We would multiply it because in order to get it twice, it means you have to have it happen first and second times. So that would require multiplication. Are these events independent or dependent? What do you think, Lana? If you flick the spinner and get whatever, does the first flick of the spinner in any way affect the second?
No.
No. So they would be independent events. Right? Questions on this? Do you see how to kind of read the problem and discern, okay, do I need to add or do I multiply? Because so far as we've worked through each section, class, it's all been you're adding on all of these. Now you're adding, subtracting the overlap on all of these. Now you're multiplying all of these. We're about to work a section where you multiply all of these, but you have to account for the fact that some are already missing, right? Like it just keeps being section by section. You did have a homework assignment a couple nights ago where it was a little bit more mixed up. You had to think it through. But I want you to be ready to think these through because quizzes and tests, it's not going to be all the same kind. You're going to have to think through, what do I do? Do I add? Do I multiply? If I'm adding, do I have to subtract overlap? If I'm multiplying, do I have to lower the numbers on the second one? You have to be able to think these things through. Turn the page. Turn the page. Let's take a look at some of these, though, that deal with the dependency of the first event affecting the second. Read number 9 all the way through part A, if you would. Joshua?
A jar of marbles contains 3 yellow, 5 green, and 2 purple marbles. 2 marbles are randomly drawn from the jar, and marbles are not replaced before the next draw. What is the probability of drawing a yellow marble, and then a green marble?
How many feel like they copied this problem from the last lesson and just changed the word to not replaced? How many think it was pretty much a copy and paste job here? That's kind of what I'm thinking. And you know why? Because that's what I would do, because I'm lazy. Yeah, so anyway, we want a yellow marble, then a green marble. Add your seats. Now I'm really curious. I'm actually going to flip back, in fact, and check this. No, they did purple, then green.
Oh.
Really?
It's the same number.
It is the same numbers, but they changed the part A, B, and C. I wouldn't have even done that. They're not as lazy as me. I am more of a mathematician. Okay, I don't know about that. They're just less willing to be boring. I don't care about being boring. Put Glenn to sleep. I don't care. Let him sleep. I mean, well, not really. Not allowed to sleep.
We're just doing A.
Just do part A. All right, so what's the probability of yellow, Lana? 3 to 10. After yellows come out, what's the probability of green, Lana?
5 to 9.
5 to 9. We can do a little bit of canceling here to get 1 and 3, 1 and 2, so the probability should come to
1 to 6.
1 to 6. How many had 1 to 6 for part A?
I got 15 and 90, and I didn't reduce it.
Okay, gotcha. Yeah, so make sure we reduce, because 15 and 9, I mean, you could divide them both by 15 if you know your 15 times tables. kind of like if you picture a clock, right? 15 times 1 is 15 minutes, times 2 is 30 minutes, times 3 is 45 minutes, times 4 is 60, times 5 is an hour 15, which is 75, times 6 would be an hour and a half, which is 90 minutes. I mean, maybe you can think through 15 times tables using a clock, but probably reduced by canceling. What about back-to-back purples? What about back-to-back purples? Part B. Back-to-back purples. All right, Scott, first purple.
1 to 5.
2 to 10 or 1 to 5. Second purple.
1 to 9.
1 to 9. Now, I will say the advantage of leaving 2 to 10 initially is you can see to drop the 10 down to a 9. That's the only upside. And then maybe you reduce later. Either way, you get
1 to 45.
1 to 45. And you're like, that sounds a lot like the 2 blues in the last jar. Yeah, I know, because there were 10 marbles, 2 of them were blue. Now it's 10 marbles, 2 of them are purple. Still 1 to 45. All right, do we get 1 to 45? All right. Yellow, then green, then purple. Yellow, then green, then purple in that order. Not just a yellow, green, and purple, but yellow first, then green, then purple. We want specifically yellow, then green, then purple. And Joshua, what's the probability of yellow?
3 to 10.
Then, what's the probability of green?
5 to 9.
And then, what's the probability of purple?
2 to 8.
2 to 8. Now, we can do a little bit of reducing. For instance, 2 and 8 can immediately reduce to give us
1 to 4.
1 to 4. The 3 and 9 can reduce to give us,
1 to 3.
and the 5 and 10 can reduce to give us.
1 and 2.
So our probability is
1 to 24.
1 to 24 chance of getting yellow, then green, then purple. All right, number 10. Lana, go ahead and read that for us.
A gumball machine contains 100 gumballs with the following flavors: 30 grape, 20 strawberry, 10 watermelon, and 40 cherry. The gumball machine randomly gives 1 gumball each time. What is the probability of receiving
A.
strawberry, then grape?
At your seats. Find the probability of strawberry followed by grape. Lana, what's the probability of strawberry?
20 to 100.
20 to 100, all right? What's the probability, after strawberry's already been taken out, what's the probability of grape?
30 to 99.
Good, 30 to 99. We do want to reduce here. I would say just knock off zeros first. I could also reduce now the 2 and the 10, Lana.
1 to 5.
1 to 5. I could reduce the 5 and the 30.
To get 1 to 6.
And I could reduce what out of both 6 and 99?
3.
3 to get...
2 to 33.
And so my answer is
2 to 30.
2 to 33. A lot of fraction reducing here, isn't there? All right, but 2 to 33, how many have that answer? All right, question.
Because when, after, why would it be 99 since there's 30 grape?
Well, there's still 30 green, right? No green came out. But of the 100 gumballs that were in there, if a strawberry came out the first time, there's not 100 gumballs anymore. There's only 99 of them. There's still 30 strawberry, right? All the 30 grape are still in there. But there's not 100 because one of the strawberries is missing. There's only 99 gumballs now. Does that make sense? So we don't lower this number, but we do have to lower the total number. Now on the next one, Joshua, because it's not different flavors, it's cherry, then another cherry right after it. Now the total number changes, but so does the number of available cherry. Does that make sense? Once one cherry's gone, there's now fewer cherry. Once one strawberry's gone, there's still the same number of grape, right? So does that make sense? All right, go and do part B. 2 cherry gumballs. This one isn't going to reduce as well. 2 cherry gumballs. Probability of cherry times the probability of cherry after cherry. So Joshua, what's the probability of cherry on the first one?
40 to 100.
40 to 100. But once you've got that first cherry out, what's the probability of another cherry now?
39 to 99.
39 to 99. Now we can do a little reducing here. What could we knock out of the 40 and 100, for instance?
The first 0.
Right, knock out the zeros, and then we can also knock out a
2 to both. To get 2 to 5.
all right. And there's something that we can knock out of the 39 and 99, but you can't just knock off the 9, of course. Okay, Scott's over there like, man, he knows that.
A 3.
A 3 to get
13 to 32.
and that's all that reduces, nothing else. So we have to multiply across the top to get
26.
and multiply across the bottom to get
165.
good. There's a 26 to 165 chance of getting a cherry and then another cherry. Now, the lowest probability class in this gumball machine is obviously watermelon. But maybe you really like watermelon. And you want back-to-back watermelon. You understand it's going to be a pretty tall order, right? Let's see what the probability is. Back-to-back watermelon. So probability of watermelon times the probability of watermelon after watermelon. He's so excited about watermelon, he couldn't keep the book on his desk. Tell you what I liked. I worked the camp store at a Christian camp summers, and the last 2 summers we were up there, we had a slushy machine right there at the register. And like sour apple, it's all right. Blue raspberry, most people's favorite. And then we got watermelon flavor. Cherry, was good, but watermelon, man, I like the watermelon slushy. And it's right there next to me. I definitely spent more than I should have on watermelon slushies. But yeah, it's good. Anyway, all right, so probability of the first watermelon. Scott?
1 to 10.
1 to 10, technically 10 to 100, right? Then after that first watermelon's gone, I'm going to go and write 10 to 100 for reference. Now what's the probability of another watermelon?
99.
Good, 9 to 99, or
1 to 11.
1 to 11. So what's the probability of getting back-to-back watermelons out of this machine?
1 to 110.
1 to 110. Highly unlikely you're getting back-to-back watermelons. Can we get that?
Yes, but on the last one, I'm just saying, but like, I wrote 40 to 100, and then I reduced to 2 to 5, and then I put 1 to 4, like, because I reduced.
You're talking about the 2 cherry ones.
Yeah.
Okay, so let's go back real quick. We had 40 to 100, and we had 39 to 99, right?
Yeah.
Okay.
And then I reduced.
You reduced this and got 2 to 5, you
2
said.
to 5, and then instead of reducing 39 to 99, I just reduced, 2 to 1, and then 5 to 4, because you take one away.
Oh, you reduced,
Yeah.
you subtracted 1 from each of these?
Yeah.
Ah, okay. So as a quick reminder, Lana, if you have, for instance, 5 15ths, what does this reduce to?
1, 8.
No, Lana, 2 12ths. You just subtract 3 from both of them, and you get 2 12ths, right? No, you know that's not true.
Yeah.
You never subtract, you always divide, right? So that was the mistake. In subtracting, that was the mathematical error. You can't subtract from top and bottom, you divide from top and bottom.
Yeah.
Make sense? All right, let's move on. Number 11. And Lana, read it for us through part A.
A bag of tiles contains 1 tile for each letter of the alphabet. 2 letters will be drawn without replacing the first. What is the probability of
It's a fun
drawing?
word. Go ahead.
What is the probability of drawing A2 vowels?
All right. Now again, from yesterday, we're going to assume that Y is not a vowel. Okay, we're going to assume that A, B, C, A, B, C,
Wow.
A, E, I, O, U are your vowels. Okay, so that's how many, class?
5.
5. But you're not going to replace. So, find the probability of back-to-back vowels.
You're not replacing?
You're not putting the first vowel back. So assuming you get a first vowel, and then you want to get another vowel after that first vowel, what's the probability? Come on, don't sneeze all over Scott. I'm going to wash that jacket later. All right, probability of the first vowel, Lana.
5 to 26.
All right, now, after the first vowel's been pulled, probability of another vowel.
4 to 25.
Let's do some canceling.
25 to get 5, and then 5 to get 1, and then 4 to get 2, and 26 to get 13.
And that gives us anyone?
2 to
65. 2 to 65. 5 times 3, 15. Carry the 1. 5 times 1 plus 1 is 6. 2 to 65. All right, what about two consonants? This should be a lot higher probability, right? There's a lot more of them. Okay, so find the probability of consonant and then another consonant. I'm just going to do C because I'm too lazy to write the whole word consonant. Then I can't always remember how to spell it. Back-to-back consonants. What is the probability? Scott, what's the probability of getting just a consonant?
21 to 26.
All right, but after you've drawn a consonant, the probability of another consonant drops to?
20 to 25.
Fortunately, there's a little bit of reducing we can do.
4 to 5.
And there's a little bit more we can still do.
2 and 13.
All right, so what's the probability?
42 to 65.
42 to 65, probability of back-to-back consonants. All right, questions on that? All right, now, how many of you have played Scrabble before? All right, upwards, games like that. Okay, so it's similar except you can stack tiles on top of each other, which makes for interesting things. But anyway, you don't want a cue. Now, Q's worth a lot of points, so maybe if you can come up with a way to do it, but like especially in upwards, man, that Q, it's only worth the same as everything else. You don't want the Q. So, what's the probability you don't get a Q either time? Just no Q's. Probability of not Q. So again, we would say the complement of Q. And then the complement of Q after already getting the complement of Q. I'd say the odds are in your favor, wouldn't you? (12 to 13) chance you're not getting a Q on either draw. Now, what would be the odds then? Let's think about it. If the probability of no Q at all on either draw is 12 to 13, what's the probability you do wind up with a Q on one of your draws then? 1 to 13, right? That would be the opposite. Getting the Q one time is the opposite of not getting it either time. So 1 to 13, the complement of this would be the actual probability of getting a Q. And remember, way back when we talked about possibilities, the possibility of getting at least 1 is the complement of the probability of getting nothing. So kind of coming full circle there. Number 12. Scott, read it through part A.
A deck of 30 cards contains 10 cards for each of the colors red, green, and blue, numbered 1 through 10. Cards are not replaced before the next draw. What's the probability of drawing the red and then the blue?
All right, this is not like any card game I recognize, but that doesn't matter. At your seats, red, then blue. Scott, what's the probability of red?
1 to 3.
Good. 10 to 30, which is 1 to 3. What's the probability of blue after red?
10 to 29.
10 to 29. All 10 blue are still there, but there's now only 29 total cards. That obviously does not reduce. And what is our answer?
10 to 87.
10 to 87. Probability. Did we get that answer for part A? Again, avoid the temptation to lower the blue to 9 card option. All 10 blue were still there. Drawing a red doesn't affect the blue, it just affects how many total were in there. Does that make sense? That's why the previous problems were 2 consonants, 2 vowels, 2 cherry, 2 watermelon. The number available kept changing because it was back-to-backs of the same thing. But here they're 2 separate, so still 10 available each time. How about back-to-back reds, though? Back-to-back reds. Lana, what's the probability of the first red?
10 to 30.
10 to 30. What's the probability of another red right after that?
9 to 29.
9 to 29. We can reduce, of course, the 10 and the 30 to get,
1 to 3.
but we can also reduce the 3 and the 9 to get.
1 and 3.
So our probability is
3 to 29.
3 to 29. We could go on back-to-back reds. All right, now, this is fun. Probability of all 3, remember these are numbered as well as colored, right? Probability of all 3 10s, one right after the other. This is why if you got all 3 10s in your hand to start out, someone would think you were cheating. Remember the short lifespan we talked about? How many 10s are in the deck, class? 3. A red 10, a blue 10, and a yellow 10. So Joshua, what's the probability of the first 10?
1 to 3.
Well, it's one card, it's 3 possible cards, right? Any one of the 3 colors of 10 out of 30 total. So what's the probability of the first 10?
3 to 30.
3 to 30 or 1 to 10, right?
Yeah.
Remember, there's a 1 through 10 red, 1 through 10 yellow, 1 through 10 blue. So that's a 10 red, a 10 blue, and a 10 yellow. It's only 3 total cards that have 10s on them. Okay? So you're good.
Oh.
Sorry, your face was telling you were confused. You got it or you
Yeah,
good?
I got it now.
You got it? You're confused.
No, I get it now.
Okay. All right. Now, we want another 10. What's the probability of getting another 10, Joshua? Let's just say it's the blue 10. Doesn't matter which one, but one of the 10s we now have in our hand. What's the probability of drawing another 10 out? How many 10s are still in the deck?
There's still
2 more, right? There were 3 to start with. We pulled 1 of them, so there's only 2 more. How many total cards are still there in front of us?
9.
There were 30 cards.
Oh, 29.
29. And then, Joshua, after we've already drawn 2 10s, we want another 10. Well, how many 10s are still left in the deck?
1.
Only 1. How many total cards still in front of us?
28.
28. Okay, so let's reduce. The 3 and the 20 and the 30 gives us
1 to 3. I meant 1 to 10.
1 to 10. I can cancel the 2 with the 28 to get
1 to 14.
1 to 14. So the top is easy. 1 times 1 times 1, of course that's just 1. And across the bottom, 10 times 29 times 14, anybody? I'm cheating and looking in the answer key because I'm lazy. $4,060. 1 to 4,060 is the odds of getting all 3 10s in successive draws. In other words, you get all 3 10s, they gonna think you're cheating. All right, questions on that? Questions on that? Turn the page, or look across the page rather. And do numbers 13 through 17. Notice there's some ors and there are some ands. So kind of a mixture of different probabilities here. Page 397, numbers 13 through 17. I tell you what, we'll take a look at these in our next lesson since time is out. I know Scott finished, the rest of you working on still a few more of them, so we'll look at more of these next time. Your homework for this evening is to do page 398, numbers 1 through 9, page 398, numbers 1 through 9, and go ahead and finish up this exercise, page 397, 13 through 17. So finish up what we were working on for homework, and then also do page 398, numbers 1 through 9. So whatever you had left of page 397, 13 to 17, we'll go over all of them tomorrow, and page 398, numbers 1 through 9. And we'll be reviewing probability tomorrow and looking ahead toward a quiz in the next lesson after that. Have a wonderful, for Monday, yeah. All right, so have a wonderful rest of your day, and you are dismissed.
What do we have?